Recording is on.
Okay, it's all yours.
Okay. Uh, so the project was to create a exact term match text search engine. So we would have three types of search. That would be a prefix search, like this, a suffix search, and a contained search. I think this would be a better example right here. So a contained search meaning that the search term cannot come as a result. It cannot be a prefix, nor can it be a suffix. It must be in the middle only. Suffix search can only be a suffix. It cannot be the exact term match itself, and same for the prefix as well. So
Just a small,
we
sorry,
have
sorry to interrupt you. Just a small note. The in the particular case, let's say contains could also give a result if you using the Z string. So if you have X Y Z, and if you are looking for X Y Z, it is produce. I mean, it should produce result because okay, it is contained in full, but
okay,
as a terminology, it is contained.
okay,
And the same
yeah,
I mean the same applies that if you do prefix and suffix but on the whole word, yeah, word indeed they should give you the result because
yeah,
actually it's a particular case, but it respects, let's say, the definition.
yeah. I saw the I had a more strict approach toward these rules.
Yeah, it's not a
Yeah, I
problem,
guess
it's okay.
fix it. Yeah, and we have two search scopes as well. One is searching for characters in a word, and the other one is searching for words in a line. So for when we're searching words, we would return the line as a result. And for when we are searching characters, we would return the word as a result. Other things to take into consideration was the constraints, meaning that a word can have a maximum of 255 characters and a line can have a maximum of 32,000 characters. So my approach that I took towards making this search engine was, let's go to the readme. Okay. So these are the tools that I used. I used the tree data structure for the prefix search, and I used the tree data structure with reverse string matching to do a suffix search, and I used n-grams for contains. I did an implementation for a suffix tree and also a radix tree, but they weren't as performant as I wanted. So I just opted to go for the tree implementation, the try implementation instead. So how the system would run would be initially we have our compile phase, and in our compile phase, what we would do is we would take the data set and we would serialize it into we would fit it into our data structures. That is, for example, we'd serialize it into a try tree. Then we would serialize it and store it for later use. I'm using Bing code for this purpose because sometimes if the dataset is too large, using Serde JSON to serialize it and put it as a JSON format is going to be uh, very costly and for it's going to be very costly for memory purposes or for storage purposes. But Bing code, uh, we use Bing code to serialize and store it. We store it in a binary format, in a U8 format. So that makes it more storage efficient. And so I just decided to go for this one rather than Serde JSON. Of course, Bing code and Serde JSON use Serde uh, as the underlying, as like, let's say the backend. Uh, so I decided to go for this one. Mm, okay.
Yeah, I think it
I
was a
decided
good choice. Yeah, good choice.
Uh, Thank you. I decided to use Ratatouille for augmenting UI experience. Probably this is a decision that I probably regret. I should have went with just using the CLI, but I just decided to use. I just wanted to create a TUI. So this is what Ratatouille is. It helps you create an interface in the terminal. So it's basically like EGUI for terminals. So I decided to go with this one, and I didn't have enough time to add this error implementation, but I was planning to use this error. And for relevance ranking, I decided to go with Levstein crate. There's already a crate for it. So basically, what Levstein distance is so you can go to the wiki and okay. So what Levstein distance is, at okay. So let's say if we have two terms, ABC and ABD, Levstein distance is the minimum amount of additions, deletion, or addition that I have to do for either one of these terms to match the two terms. So let's say if I have ABC and I have ABD, that means I have to do one edit. So this would mean that the Levstein distance would be one. And let's say if I have ABCD and I have ABE, that means I would have to edit E into C. Then I would have to add this. That would make it that would give it a value of 2. So that's how Levstein distance works. I went for using Levstein distance instead of other options like, for example, if you see um, the Tantivi, what they use at Tantivi, they use the BM25 scoring to rank relevance. I think they also use Levstein distance. I opted to use Levstein distance because for our text search engine, what we are doing is an exact term matching. So we're like, doing an exact term for prefix, suffix, and contains. And there isn't any other context aside from that that we should take into account. So I just saw that Levstein distance was a more fitting approach, so that's why I took that. So yeah, there's the wiki, and that's what it basically explains over here. Mhm. So for the purposes of uh, parsing, if we could call it that, yeah, for the purpose of tokenization, I decided to use this crate Unicode segmentation. So what this does is it takes like a sentence like this and it just puts it into an array where it splits all the words and stuff like that. So it was pretty convenient. So I just decided to use this. Of course, I could do. It wasn't necessary, but it was a choice I made back then. So yeah, and yeah. So this is what I was. This is the approach that I took towards making the solution. So we could just run over the code really quick. Okay. So these are a bunch of modules. So we have one where we implemented the data structures. We have one where we implemented what happens at compile time, meaning this is where the serialization happens. And we have one that is for runtime, which means this is where the deserialization and the actual searching happens. This app here is, we're just using this to define it in such a way that it would run both the compile and the runtime application for us when we just run this app. So on startup, we would just need to run this specific module and it would just do the whole steps for us. But after first time load, we don't need to actually run the compile up. So I just decided to set these as the default run. So whenever I go ahead and do a cargo run, it will run this runtime. So let's get into how we're compiling it. Okay, first let's get into the implementations of the data structures. Okay, so what a tree data structure is tree data structure is the recursive data structure that has a bunch of from the root node. It has a node for each and every character in the English alphabet. And so just to explain this in a more visual way, this is what the tree data structure is. So we have a root node, and we have there's one node for A, and there's one node for B, and so on and so forth, up until the last character, which is Z in the English character. So in each node, each character has a node of its own, like this. And it continues recursively. So there's A here, and there's B, uh, and stuff like that, up until all the way up until Z. So this is what the tree data structure is. Now, the tree data structure has a complexity of n times L, which is the amount of words that we enter and the length of each word. Why? Because we need to traverse each node to find that specific word. And when traversing those nodes for that singular word, we would need to go the whole length of that specific word. So the complexity would be the length times the amount of words that we would enter. So to implement this data structure, what I did was, so I created a struct for it. This is where I use blocks for the recursive structure, and there is an is terminal. So what is terminal means is it signifies whether that word is an actual word that we're storing, and that whether it signifies whether that specific node is an actual node where a value is stored in, instead of it being just an intermediary node that we use to traverse to the actual place where the value is stored. So uh, if you explain this in a better way, so let's say I have the term end. So this would be this, right? So here, wait, we do an is terminal is true, and a. Let's say if you're storing the words a and end, we also have an is terminal is true right here. So now, whenever that means that whenever we're, but let's say there's another word here which is an, but for this one, his terminal isn't true. So whenever we transverse the tree looking for words, we will know that we didn't store a word and we only store the terms a and end. So that's what the purpose of his terminal is. And the value here, the value is going to be represented like this. And here, so this is what the value is. So whenever after we transfer to that specific node, we can see what value is stored, and that would be the whole term. And we added count. Why did I add count? I added count because sometimes we can store duplicate words like and, this, and. which are supposed to be different ends. Let's say this one is found on line 3, and this one is found on line 1. So whenever I'm searching for an end, I don't want to return only one of these two results. I want to return both of these results. So that's why I added the count. So this is our default implementation, as struct. And so this is how we did the storing function. So essentially in the storing function, we initialize all of the values and set node to self. So what we're doing here is, of course, now when we're building the text search engine, we're building it so that it could be able to handle both words and lines. So I just decided to add another character, which is an empty character, to signify a space. And I made it so that that could be the 26th node. Usually on a tree implementation, you wouldn't find the space. It would only be from A to Z. But for this circumstance, I just added a space. So, uh, are you guys following? Is it clear what I'm saying?
Yeah, yeah, it's pretty clear
Uh,
and looks good.
okay. Yeah, that's clear. Feel free to interrupt if you have a question at any point.
Yeah, sure. Um,
Okay. So what what we are doing here is when we're storing, key would be the value that we be storing into this data structure, right? So what I wanted to do was, let's say if I'm storing a key of end, I just want to make sure that all values are in lowercase because I assigned all nodes would be assigned to lowercase. And since it's a box, so ideally what we would want is A to have a usize value of 0 and B 1 and C 2, and that be like an array for that like 24 and space like 25. So what I did was, instead of assigning a like specific usize to each and every one of these characters, what I decided to do is I just turned them all into lowercase, and I decided to subtract the byte values. So I think we could see. And okay, so why I'm subtracting the byte values is because I want to assign A to the zeros position and C to the second position. So so we could see here that A is like 97. And if I want to enter B, which has a value of 98, I would need to subtract both of these, and I would get a value of 1. So I could just insert it at the second position in that array. So I just decided to do this, to insert. And so now what I did here is I did a check as to whether there aren't any child nodes in that specific tree, meaning that no value has been stored beforehand. So that means that I will need to initialize the children. So because this is an option, it would be non-value beforehand. So I initialize this over here, and I transversed into that child node. Let's say if I'm storing A, I initialized it, then I transversed here. Then what I did here is I made it a terminal value. So here, when we are transversing, I think it transfers throughout, it transferred the nodes for each and every characters. And once we've reached the destination that we want to reach, we could then say that specific node that we just reached, we can make the terminal true for it. If it's already true, we could just increment the count because of the duplicate, because we want to be able to store duplicates. But if it's not true, we just push the key, the value would be the whole string, and we would make the terminal true. And yeah, so we would initialize the count as one as well, because the initial value is 0. So this is how we are storing in this data structure. And to do a search operation, what we need to do is just traverse to that specific node and see if the terminal is true or not, meaning that we actually stored a value. We actually stored that value. Of course, sometimes this node might not exist. Let's say if I only stored the term and, this node would not exist. But if I stored the term androgen, like this node would exist, but the terminal would not be true. So this is what we are doing right here is we're just traversing the nodes. So when we're traversing the nodes, even when we're searching, we have to take in account for these spaces. So this is why this is here. And if it's none, we say there's no results. So uh, we collect the words over here like this. So if the node is true and if there is some value, we would do the check right here, which was my strict uh, interpretation of what a prefix search was, meaning that it would only be a prefix of that term and not an exact term match. So I guess we could fix this by just deleting this. But okay. So, and then we would push this into a vector, which we just initialized right here. Here's the results. We push it there. So I used a flatten over here. The flatten method is used to flatten uh, recursive structures or nested structures over here. So we have a vector over here. So when we flatten it, that's what that does. And that helps me collect the words for each and every item without having to transverse every single thing. And it would just be incrementing going on to the next one, to the next one. And yeah, that's why I use flatten over here. So yeah, this is a brief overview of how I implemented the tree data structure. Uh, so if you guys have any questions as to why I did this, uh, okay. So I guess there are no questions. So for the same thing for the suffix tree as well. Um, one thing worth mentioning is that I'm using these traits in order to I'm using these traits on the struct so that we would need to signify to bin code that this specific struct is able to be serialized and deserialized by bin code. So uh, yeah, thought I mentioned that as well. So the suffix tree is pretty much the exact same implementation as the prefix tree, as the trie data structure. Of course, we use the trie data structure for prefix searches because it would be efficient for us to get the prefix of this term because we're starting from the beginning of the word and traversing all the way down. So uh, for the suffix search, what I would need to do is whenever I would want to for the suffix one, whenever I would want to store the term and, I would just reverse the string and store it as DNA. And whenever I want to search the suffix ND, I would just reverse the search term that I want to do, and I would just do a prefix search. So it's pretty much the same implementation. Um, so for engrams, Okay, I'll just explain it. Uh, okay, so for n-grams, let's say I want to store term and uh, in n-grams based on what type of n-gram I want to do. If it's a digram or a trigram, uh, or well, a monogram wouldn't make any difference. But this could be anything we want, or a quadgram or stuff like that. So let's just see the implementation for the diagrams. So if I want to store the term and using diagrams, so diagrams means, let's say when I want to store the term and, like this, A and D, diagram would be to store it in such a way that we're storing AN and ND. So what diagrams or trigrams are essentially items that are adjacent to each other. So A and N are adjacent in the word and. And since it's a diagram, we're using two characters. So A and N are adjacent and D are adjacent. But something like A and D are not adjacent, so we would not be able to store that. So what we would do is, let's say if this is the first word we're storing is end, we would say that hey, we would add on that specific diagram where that diagram is from. So this is from the first word. Let's say for the second word, let's say we are doing ND. That means we have a N here, so that means we just do this. This is for the second word. And for DE, yeah. So this is what ngram is basically. So whenever we do diagram search, we should be able to return the results. And the results will be the place where that specific diagram was found. For trigrams, it's this specific. This is what is happening. So it could be an exact match whenever we're doing ngram or diagram, but yeah. So this is this. And I say a trigram for A and D would be A and D and NDE. So in my implementation, I didn't see. I mean, we could just use ngram. We could use a diagram, trigram, or whatever gram we want to use. So let's just go over. So grams are these specific results. These are the grams. So I'm storing a hash map. I'm storing them in a hash map. So I'm storing the specific grams as a key, and I'm storing the usize that is the instance of where we found the that specific gram. Mm. So this is the first term that we're going to store. This is going to be just going to have a usize of 0 and stuff like that. So for the words, we're storing the words in a vector. So we could use this is what this would be like.
Just a question in the so in the key in the hash map is
Yeah.
what will be in the vector.
So in the vector would be the usize. So this would be the position of where we could find the words for that specific gram. So see, we're storing the words on their own vector.
I know, but
So let's say
in the key in that vector you'll have like two elements or how many elements?
in the key it's in the key, yeah, we only have one element. I
But it's a vector. I mean, in the vector, how many elements it will be?
hmm, yeah, I think I opted to use a vector because I want to handle for line searching because in the instances where we're trying to search a word from a line, I want to be able to split it into the specific words. I think that's why I use the vector here. But you're correct. I think we could just use the string and split it by white space. Well,
Yeah, because what I mean is,
uh,
if you then you need to hash the vector, no? Because in order to be using a hash map, that needs to be hash, let's say,
yeah,
with the hash and equals.
yeah,
So you would expect that that's just a simple hash,
yeah. Okay, so it wouldn't be, yeah,
because otherwise, how do you get from the map? You create a vector with those same elements, and in that case, it will match the hashing.
yeah. Uh, well, and that's it. I'm just doing an exact term match for the vector string whenever we're doing a search.
Yeah,
Then that would tell me which position I would find it here.
yeah, but I mean, you if the search query is like composed of several words, you split it by words and you put it here, or I mean, why is a vector needed and not a string? That's my I don't
Yeah,
fully understand.
yeah. That makes total sense. Uh, I think part of why I did it that way was because, let's say we want to do a search. Let's say if the engram we want to build is a diagram, is an engram that supports diagram search only, which is what this here is. And let's say I have the term and or me. And what about if I want to search the term or only, which would be it would be trying to search a single term in a place where we are storing diagrams, which would be two terms. Let's say if I'm trying to search for the word A, uh, in this one, it wouldn't try to match this. So I think in my mind when I did a vector, I used it to split this and see if A is contained in that vector. Uh,
Okay,
I
but
think the
then
for words is easy.
I know, but
You could
how
just do a contain search.
you iterate then through array and you search in the array somewhere.
Yeah.
Okay, but
Uh,
that's not performant at all. I mean,
yeah. Yeah.
normally you use a hashing, I mean, a hash map when you want very quick access to the elements, and the key is normally a simple value, let's say a number or something that can be hashed, and the access is actually O1 because internally, depending on the implementation, it has an array. Hash maps have an array, uh, and it uses the, let's say, the position of. You can see that hash code. That hash you can see it as a number, for example, and it uses the position in the array corresponding to that value, that number. So it's like
Yeah.
accessing an array by index, which is very fast. Actually, it's I think the fastest memory access. So that doesn't iterate, doesn't do anything. Of course, for performance reasons, I mean for efficiency, not for performance. For efficiency, given that you cannot allocate an array so huge, then you have a lot of gaps. Then it allocates an array of fixed size, and it does modulo size, and then it cycles, through the through it, and those are like a bucket, and then inside they have a linked list. But the first access to the position to the hash modulo uh, the size, that actually is a very fast access, is a O1.
Yeah. Yeah. Uh, yeah. You're definitely right. Uh, I should have went for the string only. Uh, yeah. Okay. We'll do that. So But the purpose of why I was using the hash mark was just to create to set the diagrams as the key, and the actual value that we want to access is the array positions, so that we can find in this vector, which are the words that we are storing, the position of where those words are. Uh, and the gram size is if we want to make it a diagram, or if we want to store it using a trigram, we could just
And what,
instantiate it over here.
and what do you store? I mean, how and is what, or you save several sizes of grams. I mean, you
Uh,
use
what if you want to store?
I mean, you use 3 gram
Okay.
or 2 gram or both. You save both.
Oh, okay.
Why I'm asking is if you're using 3 gram, for example, you cannot search for or the other way around. You cannot search for 2 characters, for example. Or if you're using
Yeah,
2 gram, you cannot search for 3 characters. I mean, you can, but the other way you can.
yeah,
Uh,
yeah.
for some
It
reason.
wouldn't allow us to do a search above the gram size. You're definitely right about that. But I did
Below,
opt out to
below the
use
gram size.
only one of these.
Mhm. So
Yeah,
you're
you
using
can
two,
only search.
no? But
Yeah,
you can search. You can search, for example, 3 words or 4 words uh, in the query. No, just you cannot search for one letter, but you can search for
yeah,
2, 3 letters, right?
yeah. I can search for anything that's at the size of the gram size and below. But for anything above, I don't think that we allow
But
to do a search.
why below? Because it should be above. I mean, if your anagram is two, then you cannot search for words of 3 characters. I mean, in the query
Yeah,
you cannot have 3 characters.
yeah.
Okay,
Oh,
but then
wait,
how this makes a search engine then? If you can only search for two, 1 and 2 characters. I mean, it should be the other way around. You're sure it's not the other way around? Because if, for example, if you store 2 grams like you do, and if you are looking for if the query is 3 characters, for example, you can engram the query. I mean, you create engrams from the query like you do from the text, and it will actually produce you 2 grams. So the first two letter and the next two letters, and then you will actually find the grams, in your index data, because those exist, and you just compare if the position is if they share the common characters. So then you know that it's around the same are one after another.
yeah, yeah. Oh, well, I opted not to do the search for when it's greater than the n prime size, because at that point, for how many types of n-gram trees would we need to generate? So
No, no,
we
no,
would need to generate one that does diagram, one that does trigram,
no, no, no,
then
no, 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 no. That's what I mean. So, for example, you can resolve all text sizes larger than your gram size. So, if your gram size is two, you can look for any larger than and or equal to two strings. You know, because you split the query string. So let's say you have AB in the text, and you are looking. I mean, you have A, B, C, D, and the other way, and then you have two graph. You will have A, B, B, C, and stuff like that. And the the text you are looking, if you say A, B, C, you can gram it. Let's say, or how should I call it? You should transform this into grams. So you split this like you do with the regular text. So you have A, B, and B, C. You have these 2 grams. So you have grams of
yeah,
size two, okay, and then you look for these two. You look for AB, you look for BC, You find them because they are in your index, in your map, because you have these two sizes, and then you need to see if these are overlapping, you know, or are one after another, by the position, because you save the position, right, of the in the
yeah,
text. And if they are overlapping, so the second character in the first one is the same with the position. The first one is the same with the position, first position in the second gram. You know these are overlapping, so you deduce that actually are the combination ABC exists in the text, which is your result.
yeah,
You know, so, and you can
yeah,
do this with any size larger than your gram size, because less you cannot. Because if you are looking for one character, for example, you don't have anywhere in your key in that map a one character save, let's say, you know. So you don't have where to search it.
yeah, yeah. That was a really nice solution. Yeah, I should have done that.
And actually, uh, with this, if you if you use it like this, so if you use like this the position and overlapping and stuff like that, you can actually end up implementing prefix and suffix query with ngram, you know, because you can for example, for prefix you just look for that string. Okay, you see the, let's say it's a two query characters, just to be simple. You find it, you know, you find a gram in your map that corresponds to those characters, and you just look at the offset. And if it's zero, it's a prefix. If it's the size of that word, let's say -2, let's say, then it's a suffix. You know, so based on the position, you know
Yeah,
where the gram is in your word. So then you can do also suffix and prefix. Okay,
yeah, yeah,
I'm just saying this because I have experience with this. That's why. So it's not like I just came up with this solution on the spot. You know, so that's why don't take it as a uh, I don't know, uh, critique and why why didn't you think of the solution and stuff, because it's reasonable, it's okay. I did it before, you know, that's why I can just say it so easily. So I did this solution before, that's why. Because what you
yeah,
did is okay, is good. Just what I'm trying to say is like or at least I'm trying to do it like this. So if I don't manage to please correct me or understand it, that I'm trying to do a constructive critique or propose a better solution in this manner, that as a learning experience, you know. Not that it's not
yeah,
okay what you did, it is. Just there are different solutions, let's say, and in which in some cases could have their advantages.
yeah, yeah. Uh, I gave up a bit too early on the greater match as well. Uh, yeah, that's a really nice solution. I'll make sure to be more diligent next time. Wouldn't be really nice to find this solution on my own, but
Yeah, but that's what just to understand. So this is like you can consider this like an advanced solution. So you could do like an iteratively to get to this. You know, not not from the first solution just to have this idea to use this. That's what I mean. So you
yeah,
don't get it in a bad way that you haven't thought about this. I mean, it would have been very hard to come up with this solution as the first solution. You know, and actually maybe it's impossible because you notice this iterative, and it's like optimization, and then you end up finding these similarities and these relations between the offsets and such, and okay, you end up with this solution. It's not, you don't just came up from the internet, you know.
yeah, yeah,
And that's
yeah,
actually
definitely.
where experience also helps, because having experience with something like this, let's say the next time you face a similar problem, let's say, or something similar, Okay, can be transformed. You can actually extend the solution, the solution that we used in the past. So then you will be able to come up with a solution, let's say a good solution, but actually your solution is based on other solutions from the past that you know and you've done. But if you haven't done those, yeah, then it's like impossible to just come up with better than those. Normally
Yeah,
you
yeah,
go through those first. So that's why it's okay. How you did just
yeah,
just proposing improvements.
yeah, yeah. No, definitely. This is why I wanted. I made it a point not to see other people's solution, just so that I could look back on this project and it would serve as a way to gauge my progress throughout the days. So yeah, I understand.
Yeah, and that's why, for example, in other calls when we had several solutions, several implementations, it helped everyone in the call, let's say, because we all learned a bit from the other solutions. So then if we were to, let's say, start over and do the implementation all over again, given that we know now the advantages of other solution, maybe a bit of this part of it from the other solution and a bit of this, and then when you combine them, yeah, you could end up with a better solution than all of other solutions
Yeah,
individually. So that actually that's the somehow that's the purpose of this call. So it's not just like do it your own and okay, just have it, but it's more like a learning experience.
yeah, 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 definitely. Uh, yeah. So um, should I continue?
Yeah, and just one for another. This was somehow the intention of this uh, topic. I mean, for the search engine, so that we become more familiar with the underlying structures that frameworks like this use, like Elasticsearch, or C, because they are somehow. This is the core of their implementation. Let's say, okay, they use more advanced algorithms too, but these are like the core ones. So yeah, it
Yeah,
helps. Yeah, please.
yeah, yeah, yeah. Okay. Uh, okay. So we're familiar with these three, and I also added uh, a type words and lines because we would have been storing words and lines in a different way for engrams.
Mhm.
We're not going to use the same method that we used for the tree where we would enter with spaces. Because beforehand, when we store the strings, we have to make sure. Okay, I'll explain. So here, let's say if the string is a line, whereas on the tree we just add a space node that we could use to transverse. Here, what we would do is if it's like and or me, I would split this into an array or and me. Then I would use these words as engrams. So let's say if I'm doing a diagram, I would do and or this would be one diagram, and I would say, hey, this is on the zeros position. Then I do or me, and this is on the first position. So
Mhm.
that's where I use Unicode words. To
Mhm.
be honest, this wasn't that necessary in retrospect, but I didn't know back then. But I could use this and split it by uh, like this, or even just use split parameters.
Yeah, just that the other one I think splits. I mean, similarly, just by multiple characters, also by various, because the uh, I think that splits also by comma maybe or other type or tab.
Yeah,
I think tab also, so space or tab and tab. I think.
yeah, yeah, yeah. So that's why I went with this option at that point in time. So yeah, I collect this as its own string per line circumstances. So that's why I'm using this enum over here to tell whether I'm storing lines or I'm storing words. So what we do here is we take the key length. If we're storing the word, we just count the graphemes. Graphemes being visible characters. That's what graphemes are. So uh, in other words, this would just be like this. Uh, yeah. So that's what graphemes are. And for lines, we're just counting this string, this that string. So counting that specific length. So if there are no words in the n-gram, meaning if this is the first word that we are going to be storing, mm, yeah, just keep a reference over here. Okay, so if there are no words in the n-gram, we're initializing a new hash map. This is where we would store our grams in. And here, what I did is, so for, sorry, so what this line over here essentially is for any one word. Let's imagine this is both a line and a word. It's okay. The possible amount of diagrams I could generate for this is we could calculate that from its length. So this is an and nd. So these are two, and the length is three. So the calculation would be we would take the length of we would take the gram size, meaning let's say what we're trying to do is get a diagram, so the gram size would be two in this case. Then we would iterate from two up until the key length. So this would mean up until let's say this is three. We'd sorry, we'd iterate from two minus one up until the key length. That means it's three. So this would result in two iterations, meaning that's the only amount of grams that are possible. Let's say if you're going for a trigram, in this case, where a trigram for end would only be a single trigram, which is end itself, this would be this would be like this. So this would mean from two up to three, and that would only be one, like one gram that we could save. So I'm using this for the purposes of making sure that we're always inside the bounds of the character that we are storing, and we won't accidentally overflow. Okay, so what I'm doing here is I'm handling the word or the word storing words and storing lines differently. So for the words, what I'm doing is I'm counting the characters in the words and I'm storing them in a string. And I do if index. Well, so index is for each item in that specific word. Uh, if index plus the n-gram size is greater than the grapheme's length, we would just continue. This is also for the purpose of us not stepping out of bounds. And what we do here is what we're doing here is essentially we have the term end, right? So we turn the whole string end into an array like this. Then here, what we're doing here is we're taking only two at a time, or whatever the gram size is at a time. And we're using the specific index position up until plus the amount of the gram size. So we would be able to extract, if it's zero, we take zero plus two. So that would be up until, so that would mean I would be able to extract the term an. And I would do that for each index in that size. Provided that, of course, the index will always stay inbound, so we wouldn't have to worry about overflowing in this case. And we would just join the whatever the results we get. So let's say here for the characters and, we're just joining it again. And as a diagram, if it's and me, or if it's this line, we're getting and you. Then afterwards, what we're doing here is we're storing it. We're storing the word that we just entered. Since it's the first word, we could do a direct entry like this. We're using the vec macro here because we already initialized it as a vector. And when we are storing it on the hash map, uh, yeah, so and when we're storing it on this hash map, we're going to initialize it as the first element, which is we found it at the first word, which is the zeros element, and we just enter the keys. The keys being the words. So yeah, the keys being the words. So for lines, what will be different is we just take the line segment, the array we just created earlier. So we did this, right, for the lines. We did an array of the words. So we would just use this instead of the whole string of the word. So that's how we're handling restoring words. That's the only difference. Um, Whereas for the words, we just take the direct key that we entered. So this is for when we're storing the first item. We can use the vec macro.
Just
As
a comment as a, so it's okay. Just a comment as a structure. I mean, uh, somehow it helps. Uh, it most of the time it helps, but if you let's say design structures or methods or stuff like that with a single responsibility. So that there is the solid principles. I'm sure you are familiar with, and there is the single responsibility. Actually, the first one principle, which actually states that, for example, instead of making a trait that has read and write methods, let's say you could have two traits individually, and each of them just handles different type of operations. And in such manner, also as a structure, it helps. For example, you could have actually different structures, one for words and one for lines, let's say, and you could create, let's say, a common one, which abstract in an abstract way it process similarly inside if it's a line or if it's a word, but you could keep then in your index two fields of this structure type, one for words, one uh, for one for lines, and then you actually look in both of them. So uh, the code is cleaner in that manner, because then you don't have this separation word lines, and also some of the code most likely it's similarly in some regards. So then because you see you have like this match with words and lines in all these methods, and in that manner actually this will be in separate, let's say, structure, or in a structure that have it in an abstract way with parameters or stuff like that, you know, for
yeah,
let's say for cleaner. But yeah, this is also, you can see it as a advanced way to structure a project of optimization. It's working like this also, just for later advanced structuring.
yeah. You're definitely right. It was a bit of a nightmare rereading the code for myself as well after I worked on it. And yeah, this could definitely use a bunch of
Yeah,
refactoring.
and you see you have, like, for example, these entry keys and modifier or insert. If you look, they are actually the same lines or very closely uh,
Yeah,
a bit low, yeah. And you actually could reuse, let's say, the code, everything or method, or even if you get the common structure, then yeah, always be the same structure.
yeah,
But this
yeah,
this comes more naturally in time. Like it's okay.
Yeah. Part of the code is kind of dirty as it is right now is because when I did this project, I only studied the Rust book up until chapter 9,
Mhm.
and I felt like I could do the project with the tools that I've accumulated, with the knowledge that I've accumulated up until that point. And I was trying to use it as a way for me to gauge my progress by the time I'd finished the Rust book, or maybe in the future, then I could just laugh. It would be a good memory for me. So I think that's definitely part of,
Yeah,
especially when I now study, I definitely see parts that I could just improve that weren't apparent to me at that point in time.
yeah. So for sure, it's good. It's good what you did, and especially uh, take into account the level of Rust knowledge, let's say you have, and or other type of patterns, let's say. It is very good what you did. Just again, just take this as a advanced, let's say, ways to do it, not that you should have done it like this from the beginning. You know, just
Yeah,
recommendations
yeah,
for future.
yeah, 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 definitely. Right. So that's for the when we don't have any items in our engram, and when we do have some items in our engram, we're still going to use this loop to check that we're inbound. And for words, if we do have other terms in that specific engram, what we're doing here is essentially all of this code is the same. Yeah, this could definitely use some refactoring. Uh, but essentially, what's going to be different over here is since we are using the hash map, uh, sorry, since we are using this hash map over here, what we could do different. Okay, what I decided to do here is let's say for circumstances where we are storing two different words, but those different words have the same grams. So let's say I'm storing the term and I'm storing the term friend. So the common gram would be ND, right? So for that case, initially when we store the term and, our hash map would look like something like this. And it would be, hey, I found this at the first word, which is end. So instead of going over and doing other stuff, what the entry method does is it helps us modify the value of that specific key. So I could just go, hey, if there's the same gram there, just want to go ahead and I just modify this value only to say, hey, I found this on the first element and on the second one. So that's what entry does. So there's the end modify method where we get to modify the value of it. Uh, so you can see this is the vec size that we're pushing onto right now. I'm using asref. Asref is a method that allows me to, uh, it essentially helps me to borrow the item. That's what it does. There's, I think, I don't know if I used as mute here, but both of those do the same thing, which is, it's a pretty useful tool. And so, yeah. So here, when I'm pushing the length of the engram at that point in time. So why I'm deciding to do that is, uh, let's say when I'm storing end, I did not first store friend, then try to store the length. What I decided to do is when I store end, the length would be one, even though length is the zeros item. So that means when I'm storing the second word, which is friend, I could just check the length, and that would be the item of where I could find friend, since friend would be the second place in the array, since one would be the second place in that specific array. So that's why I'm using the specific length at that point in time without having to push the word
Mhm.
itself. So that's what I'm doing. For lines, I'm using the line segment, but I'm pretty much doing the same thing. So this is what storing the engram is. And when searching the engram, what I'm doing here is if the search term is the exact amount as the specific engram, I'm doing just go ahead and search for the exact matches for that specific engram and get me those results. If it's less than that, just go ahead to that specific engram and make sure that it contains the term that I searched because it's below. For greater than that, we could use the overlapping solution, which I unfortunately did not use here. So that's what we're doing for the words and for the lines. Uh, and here, okay, so so that's what we're doing here. If the condition, okay, if condition is true, uh, yeah, okay. I think this means if we find if the condition is true, meaning if we're not using greater than value, then at that point in time, that means we could actually do the search. So we could go through all the words in the vector, and the result that we will return would be the one that is only a contains and not an exact term match or a prefix or a suffix one. So this was the strict interpretation of what a contains search was. Uh, so that was the condition that I used, and we just returned the results. We yeah. So this is how I implemented the trees. And now when we go as to how we do the serialization, uh, uh, I have type. So if this is a tree, this is a reverse tree. Let's just call it prefix, suffix, and the engram and search scope. So what I do is when we store the data set, we are storing the data set right here in the root directory. But for the compile module, we would need to go to its parent folder for the compile module. So we take the tomls, the place where we find the cargo manifest, and we go to its parent directory. Then we access the data set. Then here, if we are looking to store words, since we are looking to store words and lines, this is by the way how we would store it. We got a folder for the line for the ones that we use to store lines, and a folder for the one that we use to store words. So this is how we do it. And here I did the chosen scope. So this is us tokenizing with that specific constraint in mind. And this the limit is the amount of characters that we talked about that you defined on the document over here. I think uh, uh, no, yeah, over here. So what we do here is we store the trees. When we store, we just initialize and we just iterate over each value in the data set. And if it's greater than the limit, we don't store it. So that's how we're implementing the constraints. And we store it and then we encode it so that we have our binary format over here. So that's what we're doing for everything over here. For the case where we use an engram, if you remember on the struct, we defined the search scope here. So when doing an engram, we just have to add a search scope for it. So if it's a line, we initialize the search scope as a line because the default value is a word. Then we will do the storing. So that's what we're doing here. And this is us just setting the path and what the files would look like. And yeah, this is us creating this folder and this specific directory, the search, the serialized output. So we go to its parent and we just join that we just defined over here. And we write all, use write all. So yeah, this is what the completion state looks like. and this is how we are calling it. Uh, After the meeting that we had earlier this week, I can see that we can make this faster by implementing something like threads like this. This will make this step way faster, but at that point in time, I didn't know what threads were, so I just did this. Uh, so yeah, that's what compilation, the compile module looks like.
Mhm. Yeah, looks good. And
Okay.
do you have
So
a benchmark or some comparison? I mean, with the difference without threads and with threads. I mean, it should be big. Just,
oh yeah, it's like half. Okay, so this is without threads, right? So uh, so okay, so this would take around I don't know 20 seconds. I wrote a benchmark for the runtime module and not the compile one because I think first time load is something that's common for many people that it would take that a long amount of time. So I opted not to create a benchmark for this one. Um, but in retrospect, I feel like I should have because uh, even Tanti we were talking. I was seeing this. They had multi-thread indexing, and I mean, if they mentioned the amount of time it takes, well, I should. Uh, so yeah,
yeah, but it's okay if you're not familiar with threads at the beginning. So
yeah.
it's fair.
So it takes this. So it's better with threads.
Yeah.
Uh,
There are so
uh,
these are the type of let's say flow that you could easily transform when using threads, but there are some flows, let's say, some other operations that, for
yeah,
example, when they depend, that's the simplest one. When they depend on each other, then yeah, you cannot, let's say, parallelize as easily.
yeah.
Also,
So
there are techniques that, for example, you could use like caching, and if different threads, if the flow on different threads could use some common data, that let's say one thread managed to generate it and the other one can just read it, that also helps.
yeah,
Okay, that helps also in the sequential case, of course.
yeah, yeah, yeah. Yeah, I'll definitely look into that. Uh, yeah, I'll definitely take my time trying to know the intricacies and the
I I
unique approach to use when
may,
using threads.
maybe you use it in the somewhere else, but there is a nice crate. It's called Rayon, and what it does, it's offering parallelism on iterators, for example. So it just has a method into par iter or something like that, and actually
Oh,
the the map array, yeah, this one, and actually the let's say you have a map, or I don't know, some operation that you apply on the iterator, and actually those are executed in parallel then. So this is very straightforward, let's say, to parallelize a simple, let's say, for loop or something like that, to doing something on an iterator, and yeah, it helps. I mean, this is like a different type of problems than fully concurrent, like Tokyo, for example, okay, which offers you quite a lot more, and but in a different, let's say, way. This is just like a simple, let's say, primitive parallelism for collection.
mm,
Mainly, it can do more, but it's mainly used for parallelizing processing of collections.
yeah. Oh,
And it's very very nice.
yeah,
It
this is
using
pretty awesome.
it is using similar algorithm, like work stealing algorithm, like Tokyo is using. So it's pretty interesting one. It's very efficient. I mean, performant. It's very performant. It's also very fast.
Okay. Yeah. Yeah. I'll definitely check this out. Uh,
So, for example, like you have, I don't know, you have like you split a sentence, a line into words, or you split a text into lines, something like that. You can
yeah.
process those lines in parallel.
Yeah. Yeah.
The, the,
Like on this.
the words you can
Yeah.
talk
Right
about
here.
with the engram in parallel and stuff like that.
Yeah. For example, on this loop, I could do it in parallel using the.
Yes, correct. Yeah. Okay, you have this.
Okay.
You have this. If token LAN, maybe that doesn't create problems. Yeah, it doesn't. I mean, if you have some conditions like these, then other because you just imagine these blocks will be executed in parallel. So let's say a map or what's inside the closure that you have in the map, or what's inside this for
Yeah.
body, it will execute it in parallel, and you could end up also in having race conditions. So you need to
Yeah. Yeah.
be careful what conditions you put there if you have like common data. But I mean that also is in standard thread usage. So yeah, it has the same problems, let's say, but somehow
Yeah.
it makes it simpler. And for example, an advantage is that if you start threads, depending of how you could end up, for example, starting too many threads, or you need to manage to start as many threads, for example, as the CPU cores you have, because it doesn't make sense if you are processing something that uses the full CPU core, then it doesn't make sense to start more than the CPU cores, because it will be worse in performance, because it will need to do
Yeah.
thread switching, which is using CPU cycles. But if you start exactly as they are, CPUs as many threads, they will actually run in parallel. And actually, okay, Tokyo also does this for advanced concurrency, but Rayon also handles this. So behind the scenes, it has like a pool of threads, and it's using the threads. It doesn't just start a lot of threads.
Okay.
So it
So it can automatically check your CPU's amount of threads.
Yes, yes. It checks at the runtime how many CPU cores you have, how many CPUs actually, how many, because a core like we hyper threading or how it's called, you end up with two CPUs, so you can run two threads at a time, and yeah, it starts as many threads as the CPUs, so then it's more efficient. Of course, if you have uh, I/O operations like reading from a file or writing to some database and stuff like that, network
Yeah.
traffic on internet, then it's okay if you start more, let's say CPUs, more threads in this manner, because it will be able to process something else while a thread is waiting. But the normal way and the better way to do this is with async programming, actually. So not with regular
Yeah.
threads, because okay, underneath they have threads, but using async programming, and also using maybe you didn't got to that part, but also using non-blocking I/O operations. So there are libraries. For example, now if you are using something that reads from the internet, let's say like accessing a page on the internet and reading the content, uh,
Yeah.
a regular I don't know, if you just open a socket or something like that, and if you just read from it, it will stay
Yeah.
in the read. So if you are using the standard sync sockets from the standard library, it will just stay in that read operation until the server responds, and the thread will actually be blocked. But
Yeah.
with the non-blocking I/O, for example, if you are using the Tokyo sockets, what they do is actually they release the thread when it's getting to a operation that normally blocks. It releases the thread can go do something else, and it notifies, let's say, back when it finishes, and then another thread actually from the thread pool could come and continue the job. And then actually you don't have blocked threads, so then all the time you can use the CPU at its fullest, fully using CPU.
Okay. Was that a Tokyo specific feature? I thought that was just something that we would have to code ourselves.
So
The unblocking IO.
Uh, it's it is, let's say, Tokyo specific. The idea is that uh, how Rust handles this concurrent programming, let's say, is they offer in language, in the language, in the Rust, they offer in the syntax, they offer your ability to use this await and async await to mark a function that
Mhm.
it could be awaited, but it doesn't actually implement the runtime. So where actually the code runs, it's in an executor like Tokyo, for example, but others too. You can use other executors. So it's outside of, let's say, Rust libraries, Rust standard libraries. So that part of actually uh, not keeping the thread blocked and releasing it and getting the callback from when it's over, that it's done particularly in the executor. In this case, Tokyo. Tokyo is using Apple. There is a library, but there are others too. But and Mio, actually Mio, no Mio is using, yeah, it's a library called Mio, and that handles these kind of events because they go quite low level in the operating system also to be able to notify with this kind of performance and efficiency.
Yeah.
But so
Yeah.
the library by itself, let's say, needs to support. And for example, Tokyo has the async implementation of sockets, for example, which does this behind the scenes. When it waits for the server, it lets the thread execute something else. And
Okay. So
actually, this is how maybe you've heard of, I don't know, big companies like Facebook, WhatsApp, and stuff like that. And they say
did
we can process millions of messages, I don't know, a minute or a second or stuff like that. With classical threads like these that are blocking the CPU, you have no chance. So only if you use these kind of approaches and you actually maximize the usage of the CPU and you don't block anything all the time. When there is something uh, waiting, let's say you release the thread and you process something else, because otherwise you don't have any chance.
okay.
I mean, this is just
Yeah.
to
Yeah.
keep in mind for the future if you when you end up implementing
Yeah.
services like this. Yeah, just these two are important to keep in mind. Async await programming or concurrent programming actually, and this is the let's say the technology and non-blocking IO. These two are very important.
Yeah.
The idea, maybe you know, but I'm just saying the difference between concurrent and parallel or concurrency and parallelism is that parallelism is actually processing at the same time on different cores, on different CPUs. So the let's say a function you call two times on two threads, it's processed actually on separate CPUs, but concurrency actually is like dividing a method, like seeing that method code as a task, dividing that in a subtask. Let's say if you could model it in a bunch of closures or parts of let's say blocks that executes one after another, and then when you execute a method like this on let's say two not two threads, because that's the idea. When you start a method like this, a task like this, when you start two tasks like this, actually the executor could use only one thread and just move from one task to another and just say take the first subtask of the first task and executes it, and then move to the first subtask of the second task and stuff like that. And actually it uses only one thread to process all this. It's like having
Yeah.
a queue of messages, let's say. But what you see, let's say if you log or something, what you see is like they are executing in parallel. This is actually similar how CPU handles on only one CPU, how you can execute two threads. They are not actually executed in parallel because cannot be, because you only have one CPU, and actually it just switch from one thread to another. That's the thread switching. And actually
Yeah.
it switch just executing few instructions from thread one, few instructions from thread two. Just here, our few instructions are actually lines of code, and the way you separate this is by a weight. You will see that when you call an async function, you need to dot the weight, and actually where you have these dot weights, all these are like sections of the task which can be then switched to from one to another.
Yeah, yeah, yeah. Oh, yeah. I'll definitely look into that. I was also watching online a bunch of YouTubers saying that async in Rust and macros were a hard thing. So I'm definitely getting ready for that challenge, and
Yeah,
I'm just trying to amass as much knowledge as I can to
Mac,
take on the challenge.
macros are a bit, let's say, if I could say, ugly, because the they are very customizable and you can do a lot with them. But the problem is that they are like Rust code. Just that the problem is that is not really Rust code, Rust compilable code, and the editor doesn't. So it's like a Rust combined with a template, but the compiler doesn't. The editors doesn't quite understand it so well. So you don't have. The benefit of fully formatting, color highlighting, so good refactoring and stuff
Yeah,
like in a regular method. And actually, what I ended up doing in many cases is I create the method, I create a function where I put the logic of the macro and then take it and put it in the actual macro, and then just substitute there the the parameters, let's say the entry points. So this is for macro rules, the ones that are with the regular
okay.
expressions and stuff like that. So, but for
Okay, so
go ahead.
for
Sorry.
macros, for macros, when the compiler processes the code, does it do something similar like it does for generics? That it like does it like monomorphize the code and replace it with the
Yes,
places that you actually use?
exactly.
Okay,
Yeah.
okay,
So it's actually taking as a template that code that you write in the macro, and it transforms it into actual Rust code. And at
yeah,
runtime, you actually have Rust code that is running, but is generated based on that a template, because actually that's like a template. So the macro is like a template with very similar syntax to actual Rust code. So most of the time it just do the substitution, let's say, of the captured parameters and stuff, but it's mostly Rust code, but not quite.
yeah,
That's the problem with the
yeah.
EAS. And for concurrency, I really recommend you to read the documentation from Tokyo, actually, because it's very good.
Yeah.
And it's they are implementing like a mini Redis and stuff like that with the protocol and stuff. But it's very good documentation. So I really enjoyed it, and it was very practical for me. I just understood very well the
Did you say Little Indian?
mini Redis, or I don't know.
Oh, okay, okay, okay. Sorry.
So it's
Yeah, mini Redis.
you maybe you know Redis, or if you don't, it's like you could
It's
say
a in-memory key value store. I
exactly.
think that's what Redis is, right?
Yeah, exactly.
Yeah.
And it's used like especially for caching and in a distributed way, so you can have several nodes. It does replication
Yeah.
sharding and stuff, and that's the, let's say, the main reason. But you can actually use it in situations where you actually want to store even data, not as only as caching. I mean, you want to persist it also. It's not designed for that. It's for mostly for caching. I mean, the type of data that you can recover from somewhere else. So ideally, you will not make your Redis your main data storage, let's say. But yeah,
Yeah.
it's
Yeah.
used actually. There are people who are using it, but it doesn't offer you the same ACID, let's say, compatibility. So the transaction, what transaction ensures you, it doesn't fully offer like a database, for example.
Yeah. Yeah. So I'm assuming you would want to use it for fast lookups.
Exactly, exactly. So just imagine
Yeah.
you have a, I don't know, a structure in your code where you, I don't know,
Uh,
store information about a person with addresses and stuff like that, and you normalize it so you can keep less in memory, but then maybe you need to access several fields and uh, access several other structures until you get to your data, and maybe you need to do some operations meanwhile. But in order to make that fast, for example, you could denormalize it or at least parts of it, denormalize it, and just keep like you did before, keep a hash map with the actual access type of values that you care, and then you put in the values the actual okay values that you like to use, but accessing the key in the hash map is very fast. So then you end up with a very good speed. But even if
Yeah.
you but in some cases you could, let's say, have duplicate data, but you don't care about that because you don't replicate all in this caching structure. You just care about speed, and this is what Redis does actually. So it's offering this
Yeah.
denormalized form, because it is in a way you end up doing a bit of denormalization. So it's not it's not using the minimum space as possible like a database, for example, does. Also, as you see, for example, a good one is like you do these engrams. So if you take the
Yeah.
text that it's, let's say, the actual information, that is way less by orders of magnitudes than the actual n-gram structure that you have in storage usage. Because
Yeah.
you generate a lot of combinations there and stuff like that, and uh,
Yeah.
for sure it's using a lot more space, but you care about speed there. So that's, let's say,
Yeah.
Redis in let's say in a
Yeah.
simpler form, and they actually is pretty nice. I mean, they just take uh, they implement some basic operation in Redis, and actually the nice thing is that they implement the protocol, the communication protocol, as is with actual Reddit, with a real Redis. So they actually at some point they create a client, a Redis client, and you can actually communicate with a real Redis server. So it's pretty nice that they actually implemented the protocol. And okay, there are some libraries that they use initially, but they also go a little bit deeper in also how they process the messages. So it's a very good tutorial. I really recommend it to you.
Yeah.
It's just the quick start. You just
Yeah.
go
Yeah.
on Tokyo and just go the quick start and just follow that. It's great. It's very good.
Yeah. Like the one thing I could relate to Redis is let's say for Linux, like file descriptors, which is a lookup table for open folders. So I'm assuming that will be stored in the memory, right? So in a way, it's similar to what Redis is, as when you describe it to me right now. It's a in memory lookup table.
Uh, yes and no. I mean, uh, Redis it is thought in memory lookup table, but the file descriptors in Linux are not all loaded in the memory. Uh,
Oh, okay, yeah.
I mean, there are
Oh,
or let me think. I was thinking about inodes data, but that's something else.
yeah,
But by the file descriptor, you mean just if you open a file, right? And you keep
yeah,
the handle, let's say, that refers to that. Yeah. So those may be kept in the memory, I think, because there is actually quite small limit by default of how many file handles you can actually have. So yeah, it makes sense.
yeah,
It makes sense then to have that limit because it's actually kept in the memory. Yeah. I was confusing. I was thinking initially to inodes. Maybe you're familiar with that. So on the file system, like
yeah,
okay, like X and stuff like that, the metadata, let's say, information about files is stored in these inodes,
yeah,
let's say, and yeah, those could be a lot depending on how many files you have, and it could contain
yeah.
quite a bit of information. So yeah, that will be a lot to keep in memory.
On the disk.
Yeah,
Yeah,
yeah, that's actually saved
uh,
in a separate part of the disk. Yeah, yeah,
yeah. So my understanding of macros, just to quick over it, is I think macros are like snippets like this.
yes.
So you're just entering snippets of code like this. So I'm assuming this is what macros are, and this is how they're like defined. I saw the structure and it was something similar like this.
Yeah, and this is
So
the idea. So this is uh, it's like let's say you made a good analogy with generic. So it's like uh, you could have some placeholders for the variable names, let's say, for the parameters. And then if you are familiar with regex, then yeah, it's very intuitive because you can define how that. So instead of writing the variable name, for example, or the type or stuff like that, you can just define it by
Yeah.
by an expression, and that expression will match the actual code that you, let's say, for example, like you have the print line, the basic, the very simplest, let's say, macro. So print line, it's a
Yeah.
macro, and what you put in the parameters, then it knows how to process this, and you see that you can put various type of variables, and it knows how to process it all. And actually, you define by the expression, you define what to match, and actually then you can use those matches as a key, let's say, as you define a parameter in on a function, let's say, similarly. So you can imagine those like parameters in the function, but defined with an expression, with a regular expression.
Okay.
And it
So it's like writing a script to write code, a
exactly,
script that writes code.
exactly, because that's the idea. So
Okay.
it uses the. That's why actually it's very similar to Rust code, because it actually it's like a Rust code with some like a template, but just like a Rust code, which is a little bit parameterized, and that's the template. And actually, the compiler actually parses that and does this matching with regex and stuff, and actually replaces
Yeah.
only those parts, and then the rest is the actual Rust code that you write. So this is the simplest kind of macro, which is the macro rules. I mean, it's called like that, but
Yeah.
this actually has Rust code there, and you use the regex to capture it. And there are others. I think it's called argument macro or stuff like that. The idea is that the ones you use in Serde mostly, most of them, where you put on a structure or on a field. So the idea is that with those, instead of having the template like, you write another structure, which actually it's a classical Rust code. So it's like a processor. It's like a processor, and that instead of having the compiler parsing the code and using it as a template, you get feeded with the actual Rust code. So you get like three syntax, let's say. So you actually get parts of the code. You get like an element which is the method name, then the parameters and stuff like that. So you can take all these and then you use another, let's say, generator that actually you can emit Rust code as you want. And actually, that is
Yeah.
like a template. That is called code. Scene and code. These two are used. Scene is used for parsing the code, and code is used for emitting the Rust code. And actually, what you write in that code block is uh, similar like macro rules. So you write there Rust code plus using the arguments that you got passed from the parser, from the actual parser of the. So let's say you can put a, you can create a macro like this and put it on a structure. And for example, you have, I don't know, two fields, and it can generate like two uh, getter and setters, for example, getter and setter methods
Yeah.
for those two fields. That's a very naive example, but can generate actually
Okay.
anything. So actually, there you write the code that emits the code, that generates the code, like on the other one, the compiler does it. You know. Those are, let's say, the
Yeah.
most flexible ones, because actually you can emit what code you want. You know, you can generate Rust code dynamically. It's pretty nice what you can do.
Okay, that's really nice. So everything in this step is handled when the compiler creates an abstract syntax tree. So in the first step,
Yes, yes,
it handles all the macros and stuff like that.
yes. And it's nice with the macros that it offers you the ability to extend the language syntax. I mean, just think about that. You can create a macro like print line that you can put there. Okay, the variable names, and you see also in the printer you have a string with it's a formatted string. You can put there how to print and stuff like that, and debug and stuff like that. But you can
Yeah.
actually, given the fact that you can parse whatever it is in the parameters, you can actually even invent new keywords of the language, even invent a new language, create a language within language, create a language. So you can write there, I don't know, HTML code, and it will be you can write JavaScript. So you can have a macro that can actually process JavaScript code, and you from it you emit a
Yeah.
Rust code. So you can actually write JavaScript code there, or just you invent your language, and you can actually write it there in the macro body when you call it.
Mhm. So I can implement traits like display traits, my own custom display trait for that specific macro. So
Uh,
yeah,
no, you don't even need
is
to.
that like
You don't even need to do that. So it's like just imagining your macro will be like the print line macro. You can call it whatever you want, and whatever you put inside the call, the string that you put inside
yeah,
as a parameter can be anything. So you can parse that and you can generate from that whatever you want. I don't know. You invent a language by yourself which you only uses, I don't know, arrows and special digits, special characters and stuff like that. And every special character gets transformed, let's say, into a Rust keyword or a different keyword, or you can do anything. And, you know, it's like
yeah.
you can parse that string and you can generate Rust code from it. So from this, it's only imagination can stop you. You can do anything. Of course, that code is not valid Rust or something like this code, and most likely the editors will not know how to highlight it and format it and stuff like that. Of course, because
Yeah.
if let's say it would be JavaScript and stuff like that, the editors could be smart. But as I said, you could implement actually your own language. Of course, they don't know how to colorize that and refactor or I don't know, format it.
Okay. But it seems pretty interesting. Yeah, I'm definitely
It's a
excited
bit
to look
cumbersome.
into it.
It's a bit hard to develop macros because of this problem that that code that you write there it's not easily formatted, refactored, or highlighted correctly. So that's why it's a bit cumbersome to write them. But yeah, as a technique you could use for macro rules, just have another function, have your Rust code there, and just put it the other way and just replace some variables. That's it.
Okay. Yeah. Yeah, it definitely makes sense why they say it's a bit hard, as in it's a bit cumbersome.
Yeah, it is.
Okay. So uh, so should I continue?
Yeah, yeah. Sorry for
Okay.
the long
So this
derail.
is no, no, it's okay. This is what I was looking forward to. So, uh, um, so this is the runtime module. Here, what we do is we deserialize our serialized outputs that we stored over here, and we load them into memory. Then we do a searching. So here, what I decided to do here was, mm, okay, uh, yes. So this is part of what I decided to do here is on startup, I wanted to load all the indexes into memory. Then afterwards, when I try to do a search, I wouldn't have to be delayed because I'm loading the index dynamically. So the user wouldn't have to see uh, lag that it takes for deserializing and loading that index into memory.
Mhm.
So on startup is going to take certain amount of time because it is loading all the indexes. So
Yeah.
let's look at that function here. So here, this is the function that loads all the index. This is we're using this to see into the serialized output folder, which is in the root directory, and we're initializing it like this. And for three data structures, we did this just to say that a tree type is going to be a tree data structure, suffix type is going to be suffix one, and anagram is going to be like this. So whenever we deserialize a tree data structure that stores words or lines, we're just telling it that what we're deserializing is a tree data structure. So it should know that over here. And the same, I did this. So probably we could also use threads right here to optimize it.
Mhm.
At that point in time, I did not. So yeah, and then we collect it into a hash map that contains the string and the search index, which is the type that we just defined. So the string being the string here being the type of key that we're using, meaning the string here is three word or three line or suffix word, and reloading everything, every index into memory. So part of what I would like to be able to do in the future is if you see the amount of memory used when I'm loading everything here into index, it's just loading, it's just taking too much memory. I don't know. I feel like it shouldn't take this much amount of memory. By the way, what we're using here, the data set size is, we're using this data set, which has 466,000 words or lines. So I don't feel like this should be taking that much space, to be honest. So this is something that I would want to improve in the future because it's just taking too much space. But now, let's say if I want to make a search, it shouldn't take more, but it just loads up the results into the memory. So I can just access it like this.
Mhm. Yeah. By the way,
And
you can use perf tool, for example, as a profiler to analyze the.
yeah,
Okay, maybe you're familiar. To analyze the what's using that memory to see what structures, and then you can spot what you can optimize.
yeah,
Because
yeah, definitely.
it's let's say the basic or the most important rule in optimizing is always measure first because uh, you need to know what actually is using so much RAM, most of it, let's say, or time in processing for the CPU, because it doesn't make sense to optimize a function which I don't know. Even if it takes long time to execute, it's only called once, let's say. But other that it's very fast, it's called 1 million times, you know. So overall, in the execution of the whole flow, that matters more. The one that it's very fast, but it's called 1 million times.
Yeah, 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 definitely. That was why I was asking you guys last week about optimizations as well. But I didn't want to go into optimizations before I
Yeah, sure, sure. No.
got into the Rust book pretty well, because I'm
Yeah,
sure there are a bunch of other optimizations that come with using smart pointers like RefSet and Arc and stuff like that as
yeah.
well. So
Also as a I don't know as a when you work even if you when you work professionally the or for example sometimes you need to make a proof of concept or something. So always it's preferred first you have the functionality, let's say, so that you can see that the algorithm at least is working, have a working version, and then okay spend time and optimize and even do
yeah,
cleaner code, let's say, after that. So first it's just like keep it simple, just have it working, keep it simple, and then think about abstractizations and stuff like that.
yeah, 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 definitely.
And also there is a
Um,
like with optimization also you can never stop, let's say. I mean, you can always find something to optimize a bit more. The same is with code. You can always find something to make it, let's say, cleaner code and more abstract and stuff like that. But you also need to know when to stop there, because at some point it just doesn't make sense to just then to have the
yeah,
perfect code which doesn't exist and perfection is the enemy of productivity actually. So you need to,
Yeah.
it's hard indeed to know when to stop, but okay, this comes with time. So I even me, I cannot tell you that I always know when to stop. So sometimes I do too much, but it's in the end, I don't know, you you develop this skill, you see it, and it depends on the project, and depends on many factors. But
Yeah. Yeah.
just be reasonable. I mean, start simple and then complicate your life, because when you when you develop a program or something, in time the clients wants more and different stuff and stuff like that. So if you start it complicated, it will even get more complicated, because it will get complicated than you envision it. So that's why start simple, and then it will not complicate so much.
Yeah. Yeah. Even when I was trying to implement the suffix search, I found this radix tree, and I was trying to implement that because it had a better it was O of n instead of n times the length from the radix tree over here. And I took too much time trying to implement the radix tree. I saw myself that I couldn't do it because it was my first time trying to implement something,
Mhm.
just seeing from a Wikipedia page. And I decided just to go on with the project. And, if I didn't make that decision, I would have not ever,
Exactly. Yeah.
done this project. So,
Yeah,
yeah, I
because
definitely understand where. Yeah.
mostly for the proof of concept, because as the name said, is like you want to show that okay, such functionality is possible, and then okay, we can move on and start developing this, and then we can do it efficiently, optimize it, and stuff like that. But if you, let's say, start and do one part of the flow perfectly, let's say, but you don't finish the other parts, then you cannot prove, the concept. So you don't have a proof
Yeah.
of concept, because you cannot prove anything, because it doesn't work. That's why you start
Yeah.
simple, and yeah, in
Yeah.
times then you optimize it. But by the way, about the suffix tree, I think we discussed, or I don't remember exactly, but or at least how I used it before was, you could use actually a tree, so a prefix tree. Just you first reverse the text, so you reverse the,
Yeah.
the original
Yeah.
text, and you use a prefix tree, so it's like a back iterator. I don't know if you got to that,
Yeah.
implementing a back iterator, but it's like a regular iterator, just going the other way. You know.
Yeah. Yeah, at first did the suffix tree and I was worrying about performance. And when you told me about the reverse trick for the suffix search, which I saw earlier but I forgot about, then I just decided to do that. Even right now, if you see for the suffix tree, I'm just reversing strings and
Yeah,
using the tree data structure.
yeah, because actually, if you reverse both, I mean the word and the query, you end up with a prefix tree, prefix search,
Yeah,
prefix tree and prefix search.
yeah, yeah,
But yeah, you need to reverse both. But yeah, that makes sense. Then you would reverse the query too, if you reverse the text.
yeah, yeah. Uh, Okay, so this function loads the index, and this function we use to after we load the index, we take the hash map, then we take the user input, which is the scope, the search type, that is words or lines. The scope, sorry, the scope is words or line. The search type being prefix contains, and we take the search term, and this is something that we use to display the debug messages over here. So I think we should. So right here, we're using this one to display the debug messages. Then what I'm doing here is based on the user input, you could return a debug message searching in this specific file. And if we run into an error, we can, uh, okay. Uh, okay. This is weird. Oh, okay. Yeah. So let's say I'm doing a normal search and I'll get a debug message saying, hey, I'm just searching into this specific file, and that's what I'm doing right here. Then what I do is I load all the indexes into memory. Then after I load all the indexes into memory, right now when I get here, I wouldn't need to load them again. So it would be relatively, the experience for the user would be smooth, or when I show you guys, or when I show you guys. So yeah. Before I did this, it used to take like some like a bunch of seconds to make a search, just because I had to load the index dynamically. Uh, yeah. So what I do here is when then right here there's the search functionality. So if we are searching for a line, I just make sure that the item we're searching for, I segment that item into the word arrays using the this one, and I make sure to check that whatever result I get, let's say if it's for contains, I just make sure to reinforce the conditions. I make sure that it's not the exact same term that we get as a result, and is not the contains is not the exact same term. So this is what this is doing right here. Uh, then what I do is after I get all of the results, I use the Levenshtein crate, and this is the term that I searched, and this is the item that I got from the results array. Then I just, based on that Levenshtein distance, I just push it into a hash map. Then I sort it out. So usually when we do a search, we do a sort. It just takes the first element of the maybe it just uses A to sort. So it was pretty intuitive to do that. And I think you said to just return the top 100 results. So I just truncate the results afterwards and I return them.
Mhm.
So this is what's in the lib file. And in the main file, this is where we defined our, this is where we use our Ratatouille. So when using, so aside from the normal, like we're using this for checking time, for erroring, for checking errors, and we're also using this, okay, let me open this. We're using, we have to use diff to deserialize, and all of this right here we see most of these aside from Levenshtein and Unicode segmentation, and we're also using the data structs that is from this module. We're using the data structs just to get the
Yeah,
structs.
yeah,
Yeah. So we're doing that, and so we're using the Trover widgets. Trover widgets is just to make it, more